In this lecture, we'll study about IPv4 protocol. First, a little bit on protocol terminology. One octet is 1 byte, which equals 8 bits. So an octet and a byte are the same thing. A word is a group of multiple bits. You will see 16-bit word or a 32-bit word and things like that in the protocol descriptions. In addition, a flag is a 1-bit control function. And if this 1 bit is set to 1, we say that the flag is set. And if the flag is set to 0, then we say that the flag is clear. So a flag will be used as a control function within the protocol header. These are used in IPv4, but they're also used in IPv6, TCP, and UDP, and other IETF protocols. IPv4 packet is called a datagram. And the reason is because a datagram is defined as follows. In RFC 1594, it is defined as a self-contained independent entity of data carrying sufficient information to be routed without reliance on any other earlier sent packet. So in other words, we're talking about an independent unit that has all the control features and functionalities within it, and also it can be routed independently, not depending on former packets if they were successfully routed or not. And that's the definition of a datagram, and the IP packet was designed to be that way, both IPv4 and IPv6. Looking into the packet structure of IPv4, there is a header and a payload. The payload part will include a TCP, UDP header, and also the data part, which is the payload segment part. The essential functions of IPv4 are internetworking and routing. The IPv4 packet header contains all required functionalities to deliver an IPv4 packet to its destination, and that's why it was called a datagram. The version field tells you what version it is, and right now we're looking at an IPv4 packet. So in the version field, it'll have the binary number of 4 included inside. And in an IPv6 packet, it'll have 6 in binary written inside. Then there's the IHL, which is the internet header length, and that's 4 bits. It's the length of an IPv4 header in words. And one word here is 4 octets, which is 32 bits. The minimum value is 5. So the header minimum length is 20 octets. Then we have the DS and ECN bits. They are combined as 1 byte. First, the DS, which stands for Differentiated Services field, is the first 6 bits. It distinguishes service priority assignments. And then we have the ECN, which is Explicit Congestion Notification. These are the 2 bits. Now, these are used for explicit signaling of congestion in the network to slow down the speed of packets being transmitted when there is delay or congestion that is detected within the network. Then we have the total length field, which is 16 bits. And it tells you the total length of the IP packet in units of octets. It includes the entire IP packet. Now, because we have 16 bits, the length that we can indicate with these are 2 to the power of 16 minus 1, which is 65,535 octets. Now that's a very, very large size. But one of the things that you'll see is that we won't use that entire size, that full size. The reason is because IPv4 packet size is limited by the layer 2 frame size. For example, one of the things is the definition of MTU. It is the maximum size of an IP packet that can be transmitted without fragmentation over a medium. Now, for example, if you're using an Ethernet, well, based on the IEEE 802.3 standards, the size of the MTU is 1,500 octets. And from the positions where you can see that, from 46 minimum to 1,500 octets in the payload area is where your IP packet can go into. So therefore, in this case, the MTU for IPv4 will be 1,500 octets. In the case of Wi-Fi, which follows the IEEE 802.11 wireless local area network, wireless LAN standard, you can see that 2304 octet maximum size MSDU, max service data unit, is the MTU. And the MPDU, which is the MAC protocol data unit, this would include the frame control, duration ID, addresses, MSDU, and the FCS, which would have this type of a structure in an overall Wi-Fi frame. Then you can see in the part where it's written as frame body, it can be for a length of 0 to 2304 octets, and that's where the IP packet will need to fit in. So therefore, in this case, the IPv4 packet or IPv6 packet that will go into a Wi-Fi packet will have a maximum transfer unit, MTU size, of 2304 octets. Looking into the identification field, which is 16 bits, this is a sequence number used to uniquely identify the IPv4 packet. It is used together with a source address, destination address, and the protocol field. Now, looking down here, you can see the flags and the fragment offset. This is used in packet fragmentation. It's used to divide a packet if the packet is too large to pass through a certain network. Looking into the flags, there are 3 bits, and only 2 of the 3 bits are actually used. The bit 01 on the top is not used. It's reserved. Bit 1 is the don't fragment. And this flag is, if it's set as 1, that means do not fragment this IP packet. However, if it's set as 0, then you are allowed to fragment the packet if you need to. Then there's bit 2, which is more fragments. Now, what this does is, if you do fragment a packet, then the preceding part will have this bit set to 1, such that it will indicate that there is a following fragment part that is going to come after my packet, after this packet. And that's what this is used to indicate. Then there is the fragment offset. Now, this indicates where in the original datagram does this fragment belong to. And fragments other than the last fragment must contain a data field that is a multiple of 64 bits in length. Looking down over there is the TTL, the time to live. Now, this specifies the time length in seconds that a datagram is allowed to remain in the internet. Every router that the IP packet passes through should decrease the TTL by at least 1. TTL is similar to hop count in that term. And if the TTL field becomes 0 before it reaches the destination, then that packet will be discarded. We then look at the protocol field. This identifies the type of the next header in the packet directly following the IPv4 header. In other words, this is the header of IPv4. Now down here, right here, is where you're going to have your next header. And then after, even below, is going to be where you have your payload data part, the payload segment part. Now, right over there, the protocol field will indicate what is the next header that's going to follow this header that ends right here. Some of the protocol options are included in this table, which includes TCP and UDP, which are the most popular ones. In addition, you can see ICMP, which is Internet Control Message Protocol, and also OSPF, which is used to do the routing path setup. The header checksum includes the error detection code such that the IPv4 packet header is protected. And it does not protect the payload part of the IP packet. Errors are checked by the header checksum at each router. And this is because checking is needed because the fields within the packet do change. And when they change, the header checksum is recomputed. Some of the fields that would change by hop going through the routers would be like the time to live, which is consistently decreased, the flags, and also the fragmentation options. Now, looking at the address fields, the source and destination address of IPv4 are each 32 bits. There is class full address where class A, B, C, D, and E do exist. However, the CIDR, which is the classless interdomain routing notation, is used, much more popular now these days. Looking into the details of CIDR, this is a method to efficiently allocate IP addresses, enable IP routing. It was introduced by the IETF in 1993, and it replaces the class full IP addressing used in the internet. So, you will not see any more class A, B, and C type classes used. Rather, the CIDR notation is what dominates the IP addressing structure now these days. Why was this used? Well, the typical class A, B, C type, these classes, they created subnets that were excessively large, and they were larger than the number of IP addresses that were needed for that subnet. Due to this reason, a lot of them had unused, reserved, wasted IP addresses. And because of this problem, a more efficient subnetting and routing notation was needed. And this is why CIDR was created. It makes the internet more scalable because networks can be assigned proper subnet sizes. CIDR enables IPv4 and IPv6 address block allocations to organizations based on their actual network size and short-term predicted needs. This can be used to allocate IPv4 and IPv6 address spaces to internet service providers as well as end users. VLSM, which stands for Variable Length Subnet Masking, is a technique that the CIDR notation uses. Looking into a VLSM example, you can see this, where it is 123.234.100.56/24. This represents the IP address before the slash, and then the subnet mask. The subnet mask is represented by that /24 number that you see, which means that there are 24 ones right here, followed by the zeros that you see right here, and there are 8 zeros. If we were to map them to a decimal number from the binary representation, it would be the 255.255.255.0. The subnet size can be directly obtained from this subnet mask structure because we know that the IP address is 32 bits and we have 24 ones, so that means 2 to the power of 8, which are the number of how many zeros we have right here. So that means that 256 IPv4 addresses are in this subnet. The routing prefix can also be obtained directly from the subnet and the CIDR notation. Because we know the IP address, we know that the subnet mask is 255.255.255.0. Therefore, we can directly map the two, look at where the zeros are located of the IPv4 address field, and then we can directly know that the routing prefix is the part which has the first 3 bytes, which is the 123.234.100. That would be the prefix part. And therefore it ends with a .0 at the end. For CIDR IPv4 and v6 address assignments, the IANA, the Internet Assigned Numbers Authority, assigns Regional Internet Registry, which is RIR, CIDR blocks. These are assigned to countries and huge territories. These RIRs are subdivided into LIR, which are the Local Internet Registry subnets, which are further subdivided into subnets that fit the local network size. The options field in the IPv4 header is now what we're going to look into. This includes the options requested by the sending host computer. At the end of the option field, it also includes padding. And this is because we need to make this field right here a multiple of 32-bit words. So therefore, the padding will help to do that. These are the references that I use, and I recommend them to you. Thank you.